This
So in the
conference
previous
will now be
class, we
recorded.
started with the discussion of the interrupts, if I'm not wrong. So we have started with the next peripheral of the module, which is nothing but interrupts. So we actually started with like what exactly is the polling in the previous class. So polling is nothing but monitoring something on a continuous manner. So due to the concept of polling, we might face some of its drawbacks. Like, can you please list the drawbacks of polling? Can you please list the drawbacks of polling? Okay, so first one is loss of event. Okay, so miss of event or loss of event, right? Then inefficient power management also, right? And bad response time. So these are like the three very commonly seen drawbacks of polling, which we listed in the previous class. So whenever we have to overcome these drawbacks of polling, so let's say I don't want to miss any event, I want the action to be taken immediately whenever something needs to be identified. Then also along with that, the third thing is I want to put my microcontroller to the sleep mode. So all of that is achievable with the help of the concept of interrupts. So yesterday theoretically we understood what exactly is an interrupt. So interrupt is just nothing but a signal which is being provided to the microcontroller or the microprocessor, and when that signal will be accepted by the microcontroller or the microprocessor, so it is going to stop executing the current task. I mean, it is going to pause the execution of the current task. Then it will go and execute the interrupt handler, and it comes back to execute the next instruction. So there are two ways of interrupt handler. There are two types of interrupt handler, in fact. So one is IVT, the other one is ISR. So IVT is interrupt vector table, ISR is interrupt service routine. So in case of IVT, every source of interrupt will have its own ISR return in a specific address. So that address will be mapped in the table. So there will be a mapping done on a table which tells which ISR is available in what given address of your device. So whenever an interrupt occurs, first it goes checks the IVT and finds where exactly is its corresponding ISR available. Then it goes to the addresses and executes that corresponding ISR. But in ISR way of handling the instruction, whatever is the source of interrupt, control will always go to the same ISR. So there it is going to identify what is the source of the interrupt, and accordingly it is going to perform some action. So then we saw what exactly is ISR, what and all can be included and what not to include in the ISR. And the last we discussed was interrupt latency. Then we started knowing things with respect to our microcontroller, the PIC16F877A microcontroller. So we had to know what and all things are available in our microcontroller corresponding to the interrupt. So we started with the data sheet. So when you look at the data sheet, we got to know that the PIC16F877A microcontroller has 15 sources of interrupt. So corresponding to these 15 sources of interrupt, we started reading something called as individual interrupt flag bit and individual interrupt enable bit, also global interrupt enable bit. So I was just making a note of that in the previous class. So if you can see, I have said things with respect to individual interrupt flag bit, individual interrupt enable bit, and global interrupt enable bit. Now, for all the 15 sources of interrupt which are available on our PIC16F877A microcontroller, please understand. So for every source of interrupt, there will be an individual interrupt flag bit, individual interrupt enable bit. Now let me speak about these bits first. So first of all, out of the 15 sources, whichever source I want to use, I have to enable the global interrupt enable bit. Okay. So it is necessary that I have to enable the global interrupt enable bit. So if GIE is written with the value 1, all 15 sources are enabled. If GIE is written with the value 0, all 15 sources will be disabled. So it is something like the main power switch of your house. So for every light, you will get an individual switch. If you can observe, for every light of your house, you will get an individual switch. Apart from that, you will also have a main switch in your house. Do you agree? Yes. So main switch is like only if that is on, you can use the other individual switches. If that is not turned on, other individual switches are not going to play any importance. So global interrupt enable bit return with the value 1 is going to enable all 15 sources of interrupt. Global interrupt enable bit return with the value 0, it is going to disable all 15 sources of interrupt. So you want to configure any one of the source, you have to make use of GIE for sure. Now apart from GIE, so assume if it is the bulb of a room, apart from GIE has to be on. Okay, so GIE has to be written with the value 1. The main switch has to be on. Apart from that, you also have to turn on its corresponding switch in the room also, right? So for a bulb to glow, so there has to be a corresponding switch which you have to turn on. Only then the bulb is going to glow. And switch off, only then bulb is going to get turned off. So like that, for every sources of interrupt, there is also something called as individual interrupt enable bit. Okay, so there is also something called as individual interrupt enable bit. Now, what this individual interrupt enable bit is, it is just like a personal switch of a particular bulb. So whichever source of interrupt you want to configure, you have to enable that particular source of interrupt with its own individual interrupt enable bit also. So the names of these bits will be studied going ahead. It varies from one source to another source. So it will have global interrupt enable bit for every source, which has to be set by the programmer whenever the corresponding interrupt has to be enabled. So that is individual interrupt enable bit and global interrupt enable bit. Okay. Why would we enable all the interrupts at a time? So I'm telling, so it's like a main switch. Okay, all the 15 sources, if you want to enable, so it has to be enabled. It's like a main switch. So global interrupt enable has to be written with the value 1 if you want to use any of a source of interrupt. Not just that, you also have to use the personal individual interrupt enable bit. So just like the switches of a particular light. So even after global interrupt enable has been on, even after the main source of your power supply is on, you also have to switch the particular switch of a particular bulb. Only then the bulb is going to glow. So that way, individual interrupt enable bit. So it is like a switch for a particular interrupt. So you have to turn it on in order to use that particular source of interrupt. Okay. So that is global individual interrupt enable bit. Now apart from this, I told you in case of our PIC16F877A microcontroller. Okay. So in case of our PIC16F877A microcontroller, whatever is the source of interrupt, control is always going to the ISR. Okay. So it doesn't matter what the source of interrupt is, it always goes to the ISR. Now, how to differentiate or how to identify whether I came to the ISR because of the timer or I came to the ISR because of the let's say UART. So how to identify why did I come to that particular ISR? So that is identified with the help of individual interrupt flag bit. For every source of interrupt, there will be an individual interrupt flag bit which will be set to 1 whenever the corresponding interrupt occurs by the microcontroller itself. So the microcontroller itself is going to set the individual interrupt flag bit. So you have to check that flag bit if you came to that ISR because of that flag bit, and only then take the action accordingly. So for every 15 source of interrupt, there is individual interrupt flag bit. So these are the three major important bits which you come across out of all the 15 sources of interrupt. You can see here the global interrupt enable bit. The name of the bit is GIE. So this is a bit. It can either hold a 0 or it can store a 1. So what is this GIE is? If you can see here, it is the 7th bit of the INTCON register. Okay, it's the 7th bit of the INTCON register. Tell me, what is the size of our microcontroller? How much bit is the PIC16F877A microcontroller? It's a 8-bit microcontroller. That means the maximum size of the register will also be 8 bits. Okay, the maximum size of the register will be 8 bits. Every individual register will have 8 bits. So INTCON register is a special register that also has 8 bits. Out of that, the 7th bit of the INTCON register is GIE bit. Okay, so it is the 7th bit of the INTCON register, which is named as GIE. If GIE is written with the value 1, if set, it is going to enable all unmasked interrupts or disable, if cleared, all the interrupts. So that is what you have to remember. So GIE written with the value 1 enables all the unmasked interrupts, and GIE written with the value 0, it is going to disable all the sources of interrupt. So interrupts, it's a signal. Our PIC16F877E microcontroller has 16 different sources of interrupt. So you have to remember that every source of interrupt will deal with GIE, individual interrupt enable bit, and individual interrupt flag bit. Is that clear? Okay. Now let us configure the first source of interrupt. Out of the 15 sources available for our microcontroller, we are going to start with the configuration of the first source. Okay. Now we are talking about the very first source of interrupt. So let us configure that particular source. But along with that, you can see, I told you are going to come out of the interrupt with the help of an instruction called return from interrupt. Okay, that is RETFIE, which will help to exit from the interrupt routine. As well as by default, whenever an interrupt occurs, when control goes to the ISR, actually your microcontroller will make GIE return with the value 0. If I write GIE return with the value 0, what does it mean? If GIE is written with the value 0, so what does that represent? Yes, it is going to disable all 15 sources of interrupt. That means when an interrupt is being taken care of, it is not going to accept any other interrupts occurring. Okay. So when control goes to the ISR, the GIE bit is cleared on reset. Okay. So that will be cleared. It will be returned with the value 0. Once RETFIE instruction gets executed, that means control has come out of the ISR. The moment control comes out of the ISR, it is also going to set the GIE bit so that it is ready to accept any other source of interrupt afterwards. So it is necessary when you come out of the ISR, GIE is written back with the value 0. GIE is written back with the value 1 so that it can accept other source of interrupt. Right. So let us is GIE 0 at the starting? Actually, no. Like by default, it can be 0 itself. So it can be okay. If you want to know, I can look for intcon register. Okay, so intcon register. So I'm searching for intcon register here. Let me look at the intcon register. What GIE initially is going to have. If I can search for it. So if I can find the intcon register somewhere, that would be better. Okay, so I don't have that register table represented. Okay. Okay. So GIE, yes. So by default, it is written with the value 0. Okay. So GIE is by default written with the value 0. So whenever you have to enable any source of interrupt, you have to forcefully write GIE with the value 1. Okay. And there was another doubt. When GIE is 0, can you repeat? When it's clear, I mean, if GIE is written with the value 0, that clearly says you have disabled all 15 sources of interrupt. GIE is a part of another register. Yes, GIE is just the name of a bit. Okay. So GIE is just the name of a bit of the intcon register. It is a part of a register. So it's the 7th bit of the intcon register. Okay. What if two non-maskable interrupts has the same source? So see, that will be considered as two different sources only. Okay. So if they are coming from the same source, but two different interrupts are generated, then you consider it as two, you count it as two sources only. GIE will be same for all ISR. So in our case, we have only one ISR. So GIE is like global interrupt enable, which will be returned with the value 0. Okay. All right. So let us start with the programming. So we have to configure the first source of external interrupt. Now let us start with the external interrupt here. So under section 14.11, so we are going to start with the first source of interrupt. 15 sources of interrupt means 15 types of interrupts we can give at a time. Yes, not like at a time. Obviously, yes, you can generate 15 different interrupts at the same time. Whichever is taken, like whichever comes first will be taken care of first. So, yes, there are 15 ways of getting the interrupt generated to your particular microcontroller. Now we have started interrupts and we are going to configure the first source of interrupt, which is nothing but the external interrupt. Okay. So the first source of interrupt we are going to configure is the external interrupt. Can you please read till, okay, here. So can you please read up to what I have marked and let me know once you're done reading. Okay, hope you are done. Okay. So how many external interrupts do we have? How many external interrupts do we have? The very first question. So we have started to configure one of the source of interrupt, which is nothing but the external interrupt. Can you see how many external interrupts are available for our microcontroller? Did it say like, see, 15 is the total number of sources available as an interrupt to our microcontroller. So I'm specifically talking about one of the source, which is external interrupt. So did it specifically say anything like INT0, INT1, INT2 and all? So did it say anything like that here? No, right? 6? Okay, no. So it didn't say anything like INT0, INT1, INT2 and all. Please observe the external interrupt on the RB0 or INT pin is edge triggered. So external interrupt is happening at which pin of your microcontroller? 0 what? Which 0? Yes, it is at the RB0 pin. Another name given for RB0 is INT. So external interrupt is happening at RB0 pin of the microcontroller. Now, so far we have discussed two peripherals. Can you list the peripherals which are available at RB0 pin of the microcontroller? Can you list the peripherals which is available at RB0 pin? Yes, there is an LED. There is also a switch. Okay, a part of the digital keypad. One switch is configured at RB0 pin of the microcontroller. Do you think I can use LED to raise any interrupt? Can I provide an input to the microcontroller using LED? Do you think I can provide an input to the microcontroller using LED? No, that is not possible. So, which peripheral can I use as an external source of interrupt? It is always the switch. Okay. So, whenever you configure RB0 pin as an external source of interrupt, because there is a switch connected at RB0 pin, I can use the switch as a source of external interrupt. I can use the switch to give or raise an interrupt to our microcontroller. So please remember, I'm configuring switch which is connected to RB0 as an external source of interrupt. So whenever I press the switch, I am going to raise an interrupt. Then what it says is RB0 pin is edge triggered. Okay. So RB0 pin is edge triggered. Okay. Now we have just covered the portion of tactile switch. There is a switch connected at RB0 pin. So edge triggering or state triggering refers the same. Now tell me, what type of circuit connection is available at RB0 pin? What type of circuit connection is available at RB0 pin? Yes, it's a pull-up circuit. Now also tell me, if it is a pull-up circuit, whenever a switch is pressed, which edge are you going to identify? So if it is a pull-up circuit, which switch is it are you going to identify? Yes. So whenever a switch press is found, there will be a falling edge identified. Okay. So switch pressed, you are going to identify the falling edge. Okay. So at RB0 pin, there is a switch. Okay. So that will act as a source of interrupt now. So whenever switch is pressed, I am going to identify the falling edge. So what it says is, please understand, the external source of interrupt is available at RB0 pin, which is edge triggered. So either rising if the bit INT EDG is set, or falling if the INT EDG is cleared. So there is a bit called INT EDG, which is the sixth bit of the option register. Okay, so there is a bit called INT EDG, which is the sixth bit of the option register. So using this 6th bit of the option register, I have to tell whether it is the rising edge or the falling edge. I'm going to identify with respect to the switch which is available at RB0 pin of the microcontroller. So now I have to say it with the help of INT EDG. Which edge am I going to identify? I have to say it with the help of INT EDG. INT EDG. Now tell me, what should I write to the INT EDG to tell that I am going to get the falling edge? Yes, so I should be writing it with the value 0. So INT EDG has to be written with the value 0 in order to represent that I'm going to get the falling edge whenever the switch is being identified. So when a valid edge appears on the RB0 or INT pin, the flag bit INTF is set. So flag bit INTF is the first bit of the intercon register. Now what is the name of the individual interrupt flag bit associated to the external interrupt? So it is INTF. So INTF will be set to 1 by the microcontroller. Okay. So by the microcontroller whenever the external interrupt occurs at RB0 pin. Okay, so INTF will be set to 1 by the microcontroller whenever the external interrupt occurs at the RB0 pin. So INTF is the name of the flag bit. So I told you every source of interrupt will have individual interrupt flag bit, individual interrupt enable bit. So INTF is the flag bit which will be set by the microcontroller whenever a falling edge gets identified at RB0 pin of the microcontroller. And one more thing, the flag bit INTF must be cleared in, here I forgot. This interrupt can be disabled by clearing the enable bit INTE. So what is the individual interrupt enable bit associated to the external interrupt? So INTE is the individual interrupt enable bit. Okay. So which has to be set to 1 by the user. Okay. So INTE is the individual interrupt enable bit which has to be set by the user to enable external interrupt. Okay, so INT is the individual interrupt enable bit which has to be set, okay, by the user in order to enable the external interrupt. Okay, next INTF has to be cleared in the software in case of ISR before re-enabling this particular interrupt. So after I take the action upon an interrupt occurs, so INTF has to be returned back to 0 so that for the next time if interrupt occurs, your microcontroller should be able to make INTF back to 1 later. Are these points clear? Everybody, can you please confirm if these points are clear? Okay. Now let us write a simple program. Okay. So our simple program is whenever an interrupt occurs, I have to toggle the LED. Okay. So I'm going to write a program here. So first and the foremost thing, let me write the problem statement. So I have to toggle the LED whenever external source of interrupt occurs. Okay, so you have to toggle the LED whenever external source of interrupt is going to occur. So that is your that is the problem statement which we have to be achieving right now. So let us start with the execution of this. Okay, now to start with the execution, first and the foremost thing, as you already know, we have to start with the initialization. Okay, so first initialization, first let me start writing the main function. So void main, okay, and inside the main function I have to write the init config function call. Okay, and after this I have to write a while of 1. So what to write in the initialization, let us see. So I am going to write void init config function of type void. Okay, so void init config of type void. Now first and the foremost thing, I have to initialize the external interrupt. So I will write a separate function called init external interrupt. Okay, and that I'm going to write it in a separate file, that is external interrupt.c. This is your main.c file. Okay, so I will write the initialization of the external interrupt in a separate .c file, that is external interrupt.c file. Okay, so external interrupt.c. So first I have to do the initialization of the external interrupt, and also I have to not forget to write GIE return with the value 1. So I have to enable one of the source of interrupt. So the global interrupt enabled return with the value 1 is compulsory. Now being in the external interrupt.c file, so first I have to write the function definition of init external interrupt. Okay. Now how to do the initialization of the external interrupt? The only thing I have to do is, you see, I have to write int edg return with the value 0. So the reason I'm going to write int edg return with the value 0 is to inform the microcontroller that external interrupt occurs at falling edge. Okay, so to inform the microcontroller that external interrupt occurs at the falling edge. So int edg has to be written with the value 0. And one more thing, I have to enable the external source of interrupt. So I should write int return with the value 1. Okay, this is to enable external source of interrupt. Enable external source of interrupt. Okay, so that is it about the initialization of the external interrupt. int return with the value 1 is going to enable the external source of interrupt. int edg return with the value 0 is to inform the microcontroller that you are going to identify a falling edge at the RB0 pin of the microcontroller. Understood the initialization? Okay. Now I don't have anything to be performed inside while of 1. So whenever an interrupt occurs, I have configured the external source of interrupt. Assume I press the switch at RB0 pin of your microcontroller. So a falling edge gets identified, interrupt gets generated. Where will the control go when the interrupt gets generated? Where will the control go? It goes to the ISR. That ISR, I will write it in a separate file called isr.c file. Now, what to write here in the isr.c file is, I have to write the ISR functions definition. So, void ISR. Okay. Now, first and the foremost thing, when I come to the ISR, I have to check if I came to the ISR because of the external interrupt. So how to check if I came to the ISR because of external interrupt? Yes. So I have to write if INTF, so interrupt flag bit is INTF. If INTF is equal to 1, that means I must have entered the ISR because of external source of interrupt. So here what should I do is, I have to toggle the LED. Okay. So in order to toggle the LED, I have to do the initialization of the LED. I'll do it here. So I'll write tris D. Okay. Return with the value 0x00. And I'll also write port D. Return with the value 0x00. So the only thing I'm supposed to perform here is I have to write tris D0. Sorry, what is it? I just have to write RD0 is equal to not of RD0. Only one LED I'll consider. So I just have to toggle the LED. So RD0 is equal to not of RD0. And once I'm done toggling the LED, once I'm done taking the action, I should not forget to make INTF back to 0. Okay. So that is it with respect to the programming part. So let me show it here. So first initialization, I'm calling the init external interrupt function. So control will come here. So int return with the value 1 to enable the external source of interrupt. Int edg return with the value 0 in order to inform that you are going to identify the falling edge. So I have done the initialization of LED. Also global interrupt enable is returned with the value 1. Then in the main function, we don't have anything. So control will go to the ISR. Okay. When control comes to the ISR, I have to check if I came to the ISR because of the external interrupt. So I'm checking it with the flag bit INTF is equal to 1. So RD0 is not of RD0 to toggle the LED and INTF is made back to 0. Don't we need to make interrupt again 1? Which one, Muskan? Which bit you want to make it to 1? What about enable global and peripheral interrupts? So global interrupt enable bit is the one which we call it as GIE. Peripheral interrupt enable bit will be the one you come across going ahead for other peripherals. Why it comes to the ISR if while is empty? So we have configured an external source of interrupt. We have enabled the external source of interrupt. So whenever an interrupt occurs, control has to go to the ISR. Okay. INTF is equal to 0 after action. Why not INT is equal to 0? See, INTF is the interrupt enable flag bit which will be done by the microcontroller. So that one has to be returned with the value 0 so that next time if the same interrupt occurs, your microcontroller will be able to write INTF with the value 1. So if you make INTE with the value 0, that means you are disabling the external source of interrupt. In that case, after one time executing the ISR, for the second time, you will not be able to raise an external source of interrupt. Microcontroller is configured such that it will automatically go to the ISR. Yes, so ISR is the interrupt handler in case of the PIC microcontroller. So whenever an interrupt occurs, by default, control goes to the ISR. Ma'am, can you explain what external interrupt is exactly? External interrupt is an interrupt which you are raising to your microcontroller outside the microcontroller. So for example, if you see, here is your microcontroller. Okay, one second, I'll highlight. So here is your microcontroller. Okay, so you are going to press switch 1. Okay, and when switch 1 is pressed, you are going to raise an interrupt to your microcontroller. So microcontroller should handle that interrupt. So control will go to the ISR. Why INTF is cleared? To ensure the interrupt flag starts in the inactive state. So INTF has to be cleared so that for the next time your microcontroller is able to write INTF back with 1 whenever external source of interrupt is occurring. How can we identify different ISRs using flag bit if it's 1? So for every source of interrupt, there will be a separate flag bit. For external source of interrupt, the name of the flag bit is INTF. So for timer interrupt, it is TMRF. For UART, there is some other flag bit. So for every 15 source, there is 15 separate flag bit. Any other doubts? Can we proceed? So we don't have to call the ISR in any case. How does the system know to which address it has to go? See, ISR is a special function. Okay, in case of your microcontroller, ISR is a special function. So that gets called automatically by your microcontroller whenever any of the source of interrupt occurs. So that's a special function which gets called by the microcontroller itself. So it knows that any of the 15 source occurs, it has to go to the ISR. That is how the programming is done. If INTF is equal to 0, external interrupts are not allowed. Yes. So if INTE return with the value 0, external interrupts cannot be raised. In which register do we have INT EDG? So that is in the option register. So 6th bit of the option register. Okay. So the same code is available in the template also. Let me just load. I'm going to open the project. Can we use level here by setting? No. So INTEDG, it clearly says it's an edge triggered external interrupt. So you have to make use of the edge only. Level triggering is not possible. Okay. So external interrupt. So I'm opening the project. I'm going to open the source codes. There's a doubt. If we had two interrupts, then how can I differentiate for which interrupt it needs to go, as we flag set to 1 always when interrupt occurs? As I'm telling you, for every source of interrupt, there is an individual flag bit. The same questions, see, instead of you posting the questions for the organizer only, please make sure you are posting it to everyone so that your doubts are being clarified. And Sayed, I just answered your question. So I don't know whether you heard it or not, or that was a same question from Dhananjay Reddy also. So see, I am setting INTF return with the value 1. I am telling you, I am repeating again. For every source of interrupt, it has got its own individual interrupt flag bit. For the external source of interrupt, the name of the flag bit is INTF. For timer source, the name of the flag bit is TMRF. For the UART source, the name of the flag bit is something else. So microcontroller will always set the corresponding flag bit whenever an interrupt is occurring. So you have to check its flag bit, not some other source's flag bit. You have to check the corresponding flag bit to make sure you came to the ISR because of that source of interrupt. What does it mean if INTF is set to 1? Okay, so it clearly says here. So set or see, I please read it out here. Okay, so if INTF is written, what is it? INTEDG. So if INTEDG is being set, please read this. So rising if the bit INTEDG is set, or falling if the INTEDG is cleared. So if INTEDG is written with the value 0, it's the falling edge. INTEDG written with the value 1, it's the rising edge. So in our case, we have the first source of, the switch as pull-up circuit. So I will be identifying a falling edge. Hence, I wrote INTEDG written with the value 0. If we have two interrupts, then how can it differentiate for which ISR it needs to go? Okay, I hope you got it. Will bouncing effect will affect the interrupt as it is edge triggered. So because it is a switch, yes, it will make a small difference. Okay. So when it comes to the soft hardware, it might make a small difference. But here, because we are using a software simulated, it shouldn't cause any disturbance. INTEDG needs to be set by us by checking the circuit. Yes, so it has to be updated by us, looking at how the circuit is formed at the RB0 pin of the microcontroller. Okay. Now please look at the main code. So we have written the same. So LED array, which is nothing but port D written with the value 0x00. So tris D written with the value 0x00. Initialization of the external interrupt is done by calling the function init external interrupt. So there is only two things we have written: int return with the value 1 and intedg return with the value 0. Then your main function is kept empty. So now your control is busy executing this while of 1. Okay, just a blank while of 1. Now whenever an external source of interrupt occurs, control goes to the ISR. So in the ISR, I'm checking if I came to the ISR because of the external interrupt. Then I'm going to toggle the LED and INTF is returned back with the value 0. Is that clear? Can we proceed with the execution of this? Okay. So I'm building the project. Okay. Now please pay attention. I have built the project. Now build is going on. Okay. Now if you see, there is a small warning message displayed here. Let me scroll up in the output. Okay. So can you see the warning message here which says the function ISR is never called? Can you see the warning message that the function ISR is never called? Okay. Tell me, is it the user who should be calling the ISR function? Is it the user who should be calling the ISR function? No. It's the microcontroller itself whenever an interrupt is occurring. But your IDE doesn't know. Okay, your IDE doesn't know that this is a special function. Your IDE is treating ISR as a normal function. It doesn't know that ISR is a special function. Now I have to let the IDE know that ISR is a special function. Okay, so I have to tell this IDE, the development tool, that ISR is a special function. Now, there are certain coding guidelines which you have to follow while writing the program in this MPLABX IDE. So for that, you will be provided with user manual guide. Okay, there will be a guide provided of how the coding part has to be done. So I will take you to that guide. So you first have to look at the path where you installed your MPLABX IDE. So in my case, it is under program files. So it will either be under program files or program files x86. So I have it under here. Then you have to open the folder called microchip. Then in that you can go for same header inclusion needs to, not the header inclusion, there is some coding guidelines you follow. So then you can click on MPLABX, then the version. So it's 5.3.5. Then system. Okay, 1 second. Program files, microchip. Okay, so that was a wrong path. So I have to go to program file. Okay, then microchip, then XCA, the version 2.3.6, the documents. You can note this path. Your path will also be very similar to this. Program files, microchip, XC8, version 2.3.6, doc. Now you have to search for MPLAB XC8 C compiler guide for the PIC microcontroller. So MPLAB XC8 C compiler user guide for the PIC microcontroller. So I'm opening this document, and again this is a huge document. Please don't start reading it from the beginning. As of now, I want to tell ISR is a special function. So I will go in search for interrupt. Okay. So I'm going in search of interrupt. So scrolling down. So I have interrupts word found several places. I in fact want to talk with respect to the ISR function. Okay. So interrupt and interrupt service routine questions are discussed here in the section. Okay, let's scroll down. How to use interrupts in C program. So if you get time, you can just go through this particular document briefly. Okay. So then assembly code. How do I link bootloaders and download applications? So there are several places. Then something like this, you keep getting interrupt. How can I make my interrupt routine faster? So if you want, you can read this. Okay. Then, so all of this is talking about interrupts only. So I want to tell ISR is a special function. So I'm in search of it. So let me scroll it down still more a little. So then IVT option, then interrupt functions, then okay. Okay. So fine. I came across this interrupt specifier. The interrupt specifier indicates that the function is an ISR, and that is to be encoded specially to suit this particular task. Now see how to write an interrupt service routine. That is section 5.8.1. So if you move to that section, okay. So if you move to that section 5.8.1, writing an interrupt service routine. So first, write each ISR prototype using double underscore interrupt specifier. I will just copy this. So this is the coding guidelines I have to follow. Okay. So ISR has to be written like this. So I'll go here to my code. So before I write the ISR function here, I will write the specifier. Now, once your IDE sees the specifier, it will understand that ISR is a special function which will be called by the microcontroller automatically. So now I'm going to build a project. Okay. Now observe your warning will be gone. Okay, so now build is been successful. You see there are no warnings. Now let me show you the output. So file load hex, template, interrupt sources, external interrupt, distribute, default, production, the hex file. Now please keep an eye on the RD0 pin. So this pin you have to observe. Okay. So I am going to press the switch. Whenever I press the switch, the toggling of the LED happens. Now LED is actually in the state 0, that is off state. I press the switch, so it is in the on state. Again I press the switch, off. Again I press the switch, on. So what's happening is, when I press the switch, the falling edge gets identified at RB0 pin. So your microcontroller is setting INTF return with the value 1. So if you want, I can note down the steps. Okay. So what happens is, when uh, the switch at RB0 is pressed, okay, so falling edge gets identified. Okay, so when falling edge gets identified, so that is external interrupt has occurred. Now because the external interrupt has occurred, your microcontroller will set INTF to 1. So set means 1. Okay, then control goes to the ISR. Okay, control goes to the ISR. So what will you do being in the ISR is, okay, now control has gone to the ISR. So in ISR, okay, check if I came to ISR because of external interrupt. Okay, then if true, take action and make INTF back to 0. So this is what happens. Okay, so are those switches working as ideal? So I didn't get, Chaitanya, what you're saying. So you have configured only one switch, that is RB0, as an external source of interrupt. All other switches you haven't configured in your program, so they don't perform any operation. Is interrupt like prioritizing the event? Obviously, yes, that is what we studied yesterday. So whatever interrupt occurs, they are definitely taken care of. You want my code to be shown? 1 second. So this is the code I wrote. Okay. So I meant, do they emulate debounds? They don't perform any operation. Okay, so they are not being configured. So like you have not configured those peripherals, so they will be like in the inactive state. So even though you press, nothing happens with that particular switch. Okay. So do you people understand the external source of interrupt? If board is performing LED train and the interrupt occurs, it leaves in the middle and performs the interrupt. Yes. So if obviously that is the thing which has to happen. So whatever operation is been happening, it gets paused and interrupt has to be taken care of. Like hardware interrupt, we have non-maskable and maskable. Right now, we are going with software interrupts. Do we have any type of maskable like it in this? So what we are doing is still the hardware interrupt itself. It's not the software interrupt. Software interrupt means the ones which occurs with respect to the instructions which are already in your software. For example, the INT instruction. So there are some instructions which raises the interrupt. That is software interrupt. So we will never study any of the software interrupt in our module actually. So that you will study in your LI only. So this what you are seeing is a hardware interrupt because it is being raised by a hardware. So it's a switch, it's a hardware which is raising the interrupt. So I understand it is through software. Okay. So it is identified by the software, but the interrupt which is being raised is by the hardware. It's an hardware interrupt. Okay, applications of interrupts are in emergency or special case purposes. Yes, so whenever you have to take the action immediately upon occurrence of some event, you have to make use of interrupts. How it categorizes that it is maskable and non-maskable. It completely depends on the microcontroller. So for 15 sources of interrupt, okay, all 15 sources in fact are non-maskable interrupt in our case. So it's the microcontroller who decides which interrupt it is going to accept. Out of that, which one is the maskable interrupt, which one is the non-maskable interrupt. It completely depends on the microcontroller. Hardware means external interrupt other than occurred in the program because of external request. Hardware means which has been because of the hardware, because of some peripheral. If there is an interrupt occurring because of some peripheral, so it's a hardware interrupt. Okay. So this is nothing but how we configured an external source of interrupt, and whenever an interrupt occurs, control goes to the ISR and it is going to handle the interrupt. So that's the external interrupt, how we configured. The next we have got is to study the difference between polling and interrupt, how to overcome the drawbacks of polling with the help of interrupt. For that we have program written. So we will look into the program. Please take a break of 2 minutes and then we will continue. Okay, can we proceed? All right. Now we are going to speak about the problem with respect to the polling. So how to overcome the drawbacks of polling. So first we are going to discuss the two drawbacks. First one is bad response time. Okay. So first one is bad response time and the second one is loss of event. So these two are generally observed in case of polling, which is not happening in case of interrupts. Okay. So whenever you are using the polling, so there are chances that you might end up getting bad response time. So you may not get the response immediately. And also there are chances of you losing the event in case of polling. But in case of interrupt, whenever an interrupt occurs, it is 100% sure that the interrupt will be responded immediately. And also, if an interrupt has been occurred, so nevertheless, like not in the ISR. So if ISR is being served and an interrupt occurs, it is not accepted. So apart from ISR's execution, if the controller is somewhere else out of the ISR, and if there is an interrupt occurring, there is no chance that you are going to lose that particular event. So with the help of interrupts, you can achieve good response time and there is no loss of event identified. Now to prove this, we have a small program where the switch 1 is being configured both as an external interrupt and also as a digital keypad. So external interrupt and also as a key of digital keypad, or I would say switch of digital keypad. So what we have done is, whenever an external source of interrupt occurs, we are going to toggle LED 1. Okay. So whenever an external source of interrupt gets identified, so we are going to toggle LED 1. Okay, of port D. Okay, LED 1 of port D. And whenever a switch of the digital keypad, okay, is identified, so we are going to toggle LED 2. Okay, so we are going to toggle LED 2. So toggle LED 2 off again the port D. Okay. Now observe the program for that. So I'm going to open that program. Close this and open a new project. So that is interrupt, polling versus interrupt. So first coming to the source, if I start with main.c, you can see we have done the initialization of external interrupt. Also, we have done the initialization of the digital keypad. So if you see the functions, if you open digital keypad and external interrupt, the functions are not changing. So it's the same file which I first wrote for the digital keypad. Whatever two functions we wrote, init digital keypad and read digital keypad, it's been taken as it is. Then coming to the external interrupt, it's been returned as it is. Okay. So I haven't changed anything, even a single bit is not being changed. So that is why we call it as a driver code. Once we keep the file ready, we can just reuse it. So we don't have to make any changes to it. So this is the initialization of the digital keypad, and this one is the initialization of the external source of interrupt. Also, I have not forgotten to write GIE return with the value 1. Then coming to the main function, so I'm reading the key as a state detection. Okay. So if key is equal to switch 1, I'm going to toggle the LED 2. Okay. If key is equal to switch 1, I'm toggling LED 2. This is polling. Okay. Key equal to switch 1. I'm continuously monitoring if the key I have read is switch 1 in my while of 1. So this is called as polling. So LED2 is equal to toggle of LED2. That is RD2 pin of your microcontroller. And I have a small for loop written just to represent there might be some other statements I want to get executed after the if block. So I have a small for loop written just for the sake of representation that I may have some other tasks to be performed after this particular operation. Okay, so this is polling. We also have configured the external source of interrupt. So whenever an interrupt gets identified, so control goes to the ISR, and here I'm checking if I came to the ISR because of external interrupt, and I'm going to toggle LED 1. Okay. So switch 1 right now has been configured both as an external source of interrupt, also as a key of digital keypad. So external source of interrupt is an example for interrupt. As a key of digital keypad is an example of polling. Now I will build this project and load it into your microcontroller. So I'll go to load. Then under polling versus interrupt, okay. So polling versus interrupt. Then I have to go to distribute, default, production, the hex file. Now please pay attention and keep an eye on D0 and D1 of port D. So LED 0 and LED 1. Okay, you have to keep an eye. See, I am going to press switch 1. Whenever I press switch 1, LED 1 will definitely get toggled. Okay, so whenever I press switch 1, LED 1 will definitely get toggled. Now please keep an eye on only the first LED. I press the switch, LED was 0, LED is made 1. Again I press the switch. Please keep an eye on only the first LED. LED was 1, it is made 0. Again I press the switch, LED was 0, it is made 1. Again I press the switch, LED was 1, it is made 0. Again I press the switch, LED was 0, it is made 1. Do you see that whenever I press the switch, toggling of LED 1 is obviously happening, right or wrong? So whenever I press switch 1, toggling of LED is definitely happening. That is because toggling of LED is done inside an ISR. That means whenever I press the switch 1, external interrupt gets identified, control goes to the ISR and it toggles LED 1. So please remember, if I have used an interrupt, interrupt will never be missed and there is no chance of loss of event. So there is no chance of bad response time. There is no chance of loss of event. Every time, whenever I press the switch, LED 1 is definitely toggling because interrupt is definitely being taken care of whenever it is occurring. But now keep an eye on the second LED. I press the switch, LED was 1, it is still 1 itself. Again I press the switch, okay, luckily LED was 0, it turned out, LED was 1, it turned out to be 0. Again I press the switch, it was 0, it is still 1. Okay, please keep an eye on the second LED. I'm repeating again, LED is 0 right now. I press the switch, okay, luckily it gets turned on. Now LED is 1, I press the switch. Keep an eye on the second LED only. See, I press the switch. LED was 1, it is still 1 itself. Again I press the switch. LED is 1, it is still a 1 itself. Again I press the switch. LED is 1, it is still a 1. Don't you think I'm losing some of the events if I configure it as a digital keypad? Am I not losing some events? So true. Please understand, if I have configured a switch as an external source of interrupt, there is no way that I lose an event or there is no way that I'm getting a bad response time. But if I'm configuring it as a digital keypad, if I'm configuring it and keeping an eye on the pin, So there are chances of me losing an event because LED2 didn't get toggle every time I press the switch. I lost some of the events. I also ended up getting some bad response time. So to overcome the drawbacks of polling, we always have to choose interrupts. Are you able to follow this? Mm, aren't we losing the event due to interrupt here? No. So that is not due to interrupt. Okay, so see, I'm keeping the ISR as simple as possible. So we are not losing any event because of an interrupt here. So that is highly challenging. So due to interrupt, losing an event is not something I would consider because I have kept the ISR as simple as possible. It's the software simulated loss of event should not occur. See, even though it's a software simulator, I'm working it using a software. It is the code what I have written. Your hardware will definitely show the switch press, but your software is not able to take it. Your key equal to switch one is not able to take it. Even though it's the hardware, you are programming it. You are having a software written for it. So it's the fault of your software. I'm not saying it's the fault of your hardware. It's the fault of the program you have written. So that is why I say polling is the drawback. Polling has the drawback. I don't say the drawback is with respect to the hardware. It's with respect to the type of the code we have written. So polling causes the drawbacks and not the interrupt. When to load code in the where to load code in the physical board. So if you have a physical board, you should actually also buy a loader. Like there will be a dumping kit which comes along with the board you have bought. So that is the pick kit. So it comes with the kit, so which has to be like bought along. So that you have to use, and you just have to uh, like serially write the code. So you just have to dump the code. Can you repeat why it is losing the events in LED2? So I have configured key as a digital keypad. And for example, if your software is busy executing this for loop, or your software was busy executing this thing, and I have pressed this which your software is not able to identify it. So that is why whenever you have configured the key as a source of digital keypad, then there are chances of you losing an event because you are doing it as a method of polling, not the interrupt. As we had blocking delay, control was busy assumed for 4 seconds, until that not able to read switch. If we give switch input assumed when it is at the second, okay, so second, it can't take as it is busy in 4 seconds execution. So we are missing an event. Yes. So because of this only we are missing an event. So my intention is not to create a delay. My only intention of having this for loop return is to tell that I may have certain other operations written after this, due to which you are not able to identify the key press immediately. Sorry. Any other way, other interrupt to prevent loss of event. See, it can be any source of interrupt. As of now, we have known only first source, which is external interrupt. We have another 15 sources left. So each one of them will prove that there is no chance you're going to lose any event. Okay. So all 15 sources I cannot make you understand here itself, but definitely we have other 14 sources which are left, which also behaves the same way as that of your external interrupt. Okay. Now, can you tell me one more drawback of interrupt apart from loss of event and yes, apart from loss of event and bad response time? Any other drawback of polling we have missed out? Bad response time and loss of event. Yes, inefficient power management. Memory management is not a drawback. So memory is not being affected either by the polling or interrupt. Yes, it is inefficient power management. I said inefficient power management only because I couldn't put my microcontroller to the sleep mode in case of polling because I have to monitor something on a continuous manner. I cannot put my microcontroller to the sleep mode. But if I'm using interrupts, then I have an option of putting my microcontroller to the sleep mode. So for that, we have one more project called power management. Let me open that. So what I'm doing here is I'm trying to put my microcontroller to the sleep mode. For that, I have to first make sure if my interrupt will be able to wake the system up from the sleep mode. You can read a point here which says the INT interrupt can wake up the processor from the sleep if the bit INT was set prior to going into the sleep. So before putting the microcontroller to the sleep mode, if I write INTE with the value 1, then it is possible for the external interrupt to wake the system up. So that is what the statement says. So your external interrupt is capable of rising the system up from the sleep mode. Now, first of all, how to put the microcontroller into the sleep mode? Have you known any built-in functions which puts the device into the sleep mode? Have you studied how to use sleep in your C program? Have you used sleep in your C program? Have you used sleep in your C program? May I know how? How did you write that sleep? Sleep of 10. Okay. What did sleep of 10 do? What was that 10 inside the sleep function call? Yes, so that was to put the microcontroller to the sleep mode for 10 seconds, not milliseconds, it was seconds, number of seconds. Okay, so you could call. Guys, you people are still using organizer or presenter only, so please make sure you're chatting it with everyone. Okay, so I was telling, yes, we can put the microcontroller to the sleep mode. So in case of your C programs, you wrote it as sleep with, let's say, 10, 20, 30 specified. So that was how you were calling the sleep function. Sleep was a function in case of your C programs. And that was to put your CPU, your device, to the sleep mode. Now you want to put your microcontroller to the sleep mode. So that also has some coding guidelines. You cannot use that sleep function. So that was for the GCC compiler which you were using. And now we are using X8 cross compiler, and that sleep function will not work here in the X8 cross compiler. So I have to search for something called as the sleep. So let me search for sleep in this guide, the same user guide which I used to search ISR, the interrupt. I'm going to search for sleep here. So I want to know how to put the microcontroller to the sleep mode with the help of the X8 cross compiler. So to start with, let me come from page number 1. So everywhere it just says the word sleep. Okay, here it is directly the call of the sleep. Let me see how to do a sleep. Okay. Sleep is in fact a macro which has been included in xsc.h header, a macro that puts the device into the sleep mode. So what is the prototype? It is void sleep of void. So you just have to do the sleep function call like this. Okay, it's a macro, in fact, a function like macro. It is going to put the microcontroller to the sleep mode. So what we have done here in the project is, if you open your main.c, if you see, so we have taken LED's initialization. We have configured external interrupt. So the configuration is still remaining the same. No changes in the init external interrupt function call. Then GI is returned with the value 1, which is global interrupt enable. Then we have taken some variables. Count return with the value 5. Okay. Then I have unsigned long integer I, unsigned character variable called key taken. Now look at this and tell me how many times LED2 will be blinked. Count is initially having the value 5. How many times the LED2 will be blinked? Only once? 5 times? Okay. So count is initially returned with the value 5. So count not equal to 0. 5 not equal to 0 is true. So blinking of LED is going to happen. I mean toggling of LED is going to happen. So LED is 0. It is been made 1. Then I'm running a loop just to introduce a delay. Count minus minus is going to reduce the value of count to 4. Again you come back here. So it is if else block. So you come out of the if else block. You are inside while of 1. So count this time is 4. 4 not equal to 0 is condition true again. LED is toggled. So it was 0. It is made 1. First it was 0. Then it was made 1. Now it is again made 0. A delay. Then this count takes the value 3. So again you come here, it is 3 not equal to 0 true, LED is made 1, then count will take the value 2. So again you come here, count is 2, condition is true, then LED is made 0 again. So count is made as 1. Again you come back here, count is 1, 1 not equal to 0 is true. LED will be made 1 again. So count is made 0. Then 0 not equal to 0 is condition false. It comes to the else part. So count is assigned back to 5. You are putting your microcontroller to the sleep mode. So LED2 gets toggled for 5 times. 1 0 1 0 1 and your microcontroller is sleeping. Now before you have put your microcontroller to the sleep mode, you have made count with the value 5. Now your microcontroller has been sleeping. So whenever an external source of interrupt occurs, that is when I press switch 1, an interrupt occurs, you are going to wake the system up and your microcontroller continues to execute the code from this place. After coming out of the sleep, again you come out of the if else block. Now the count value will be 5 again. So again 5 times LED2 will be toggled and it comes to the else part and it is going to sleep. Now, whenever your microcontroller is sleeping, you are waking it up with the help of external interrupt. So control goes to the ISR and in the ISR, I am just toggling LED1 to represent that I have raised an interrupt. So I'm toggling LED1. So that is to tell you that when you have configured an external source of interrupt or any source of interrupt, you still can manage the power efficiently by putting the microcontroller to the sleep mode. So interrupt is going to wake the system up from the sleep mode. Okay. So you can see here, I'm going to load the hex file. So it is under power management, then distribute, default, reduction, the hex file. You can see LED2 is getting toggled for 5 times. So it was 10101. Now your microcontroller has been sleeping. I'm going to wake the system up from the sleep mode by pressing the external source of interrupt. Now when I press the external source of interrupt, LED1 toggles for once, LED2 toggles for 5 times, again it goes to the sleep mode. You observe. Okay, so it goes to the sleep mode. So the only thing I wanted to highlight here is you can put your microcontroller to the sleep mode with the help of sleep macro call. So it's a function like macro. Whenever you put your microcontroller to the sleep mode, you will be able to wake the system up with the help of external source of interrupt. It toggled twice. Which one? No, LED2 is going to toggle for 5 times. Toggle means on, off, on, off, on. So it did for 5 times. Then again off, on, off, on, off. So it did for 5 times. So that is toggling. Are there any other ways of to wake the microcontroller? So a microcontroller can be woken up from the sleep mode only with the help of an interrupt. It can be any other source, not just the external interrupt. It can be from any other source. Sleep microcontroller sleeps for how much hours? So it will be sleeping until you are going to wake the system up. So until you provide the power, so program like your microcontroller will still be in the on state and it will be in the sleeping mode. So you are going to wake the system up from the sleep mode whenever an interrupt occurs. How can we make the microcontroller sleep using polling? I said you cannot. So that is why we went with the interrupt. I told you with the help of polling, you cannot put your microcontroller to the sleep mode because it has to continuously monitor an event. So your microcontroller has a task to do throughout the day, that is to monitor a particular event. So because of that, you will not be able to put it to the sleep mode. So you have to use interrupt if you have to put the microcontroller to the sleep mode. So this is how we can wake the system up. Can we make sleep for a specific time? No. So for this particular microcontroller with the help of XC8 cross compiler. So if you like literally want to wake the system up, like if you want to make the device sleep for a certain duration only, then you have to use an external timer outside the microcontroller. And after that particular time is raised, you have to raise an interrupt from that external source. So for example, RTC. So you can make RTC count, you can make your microcontroller sleep, and after the time has reached, you can make your RTC wake the microcontroller up. Okay. So this is how you are going to overcome the drawbacks of polling with the help of interrupts. Understood the topic? Okay. So this is one of the source of interrupt. We have totally 15 sources of interrupt. So your other 14 sources, we will see one after the other. Whenever we discuss a peripheral, if that is raising an interrupt, then you can count it as a source of interrupt. So we will not study all 15 on a continuous manner. When it goes to the sleep mode, why is LED still on? So when it went to the sleep mode, whatever was previously provided to the port, so that has been displayed. So LED is like a separate peripheral which is outside your microcontroller. Whatever was fed to it earlier, so that is being taken care of by the LED. Okay. So no changes can be observed. If you see, nothing other things works apart from the external source of interrupt. None of the other peripherals are going to work on this board because your microcontroller is sleeping and it is not able to control any of this peripheral. So none of the other things will be working. Okay. So only external interrupt will be able to wake the system up. Yes, only microcontroller is the one which is sleeping, not the whole board. Power is provided separately for each peripheral. So yes, because each peripheral will have different voltage of working. So each one will get like the main connection will be with one power source, which will be given out to all other peripherals. What if the power supply is turned off while the microcontroller is in the sleep mode? Then the whole board is going to get turned off. Nothing is going to work. So it's like a man is sleeping. While the man is sleeping, if the man dies, so something like that. Okay. So that is about the external interrupt. I hope the topic is all clear. So this completes the interrupts topic. So we are done with interrupts as well. The next we have to start is the most important peripheral, which is nothing but timers. We are going to start it in the next class. So you don't have class tomorrow. You don't have class on Monday. So tomorrow and Monday is a holiday. So we are going to meet back on Tuesday. So you do have class on Tuesday. So you please make sure you are attending the class on Tuesday without fail. Okay. So those are not attentive here in the class. Please make sure you are informing your class people also that there's no class on Monday. So Tuesday you don't have a holiday. So from our MSG side, so we have provided the holiday on Monday. So only on Monday you do have a holiday. So Tuesday we will resume back with the class. Labs, no labs also. I'm not sure about tomorrow's lab. So did your lab mentor instruct you anything regarding that? No? Okay. So let's just check. I'll just inform her to give you any information. So tomorrow we don't have a class. We are meeting back on
Tomorrow there
Monday.
is no lab, ma'am.
Okay. So we do have a class on Tuesday. Okay. So 1 second, I'm giving you the QR. Please have your attendance mark before quitting. Thanks for attending the session. You can quit. Okay. Turning off the power supply to a microcontroller in sleep mode will result in the loss of RAM data and need to restart the program from the beginning when power is restored. To mitigate data loss or maintain a specific state during power interruption, consider using backup power sources. Appropriate power management strategies in your design. Oh, Meda is like giving a big information, so we don't have to worry about all of this. Okay, so in the background, if you literally want to understand, yes, this is what happened. So I was just giving you a fair idea from the beginning. Okay, then Nagachandran is again asking, ma'am said no lab for tomorrow. Okay, fine. Okay, so then no lab, no class. We are meeting back on Tuesday. And the template which I have downloaded from the Moodle is not working. It has to be working. Please make sure your